Close your eyes now, and let yourself settle into comfort. Tonight, we're going to explore something extraordinary, a thought experiment that will carry us through deep time, through the patient physics of planetary motion, through a transformation so gradual that no single generation would notice, yet so profound that it would reshape our world entirely. We're going to imagine what would happen if Earth stopped spinning. But not suddenly, never suddenly. There will be no catastrophe here, no disaster. Nothing to startle you or cause alarm. Instead, we're going to watch this happen the way nature prefers, slowly, incrementally, across thousands and thousands of years, each change so subtle that it blends seamlessly into the next. Think of it like watching a glacier move. If you stood before a glacier and watched for an hour, you'd see nothing. Watch for a day, still nothing. But return year after year, decade after decade, and you'd see the ice has crept forward, carving valleys, reshaping landscapes. Earth's rotation slowing would be like this, a change measured not in human lifetimes, but in geological epochs. Not in years but in millennia. This gradual deceleration is actually happening right now, as you lie here listening. Earth's rotation is slowing, has been slowing since the moon formed, will continue slowing for billions of years into the future. The change is tiny, about 1.7 milliseconds added to each day every century. You couldn't feel it. Your grandchildren's grandchildren wouldn't feel it. But over deep time, over the vast patient spans that planets measure their lives in, this tiny change accumulates into something transformative. Imagine we could speed up time, watching Earth's rotation like a time-lapse video spanning millions of years. We'd see the planets spin gradually, almost imperceptibly, slowing down. The day-night cycle that currently takes 24 hours would stretch longer. 24 hours becomes 25, then 26. Centuries pass and days reach 30 hours, then 40, then 50. The change continues, patient and inevitable, driven by forces as fundamental as gravity itself. This isn't science fiction or fantasy. This is physics. The same gravitational interaction between Earth and Moon that creates ocean tides also creates friction, and that friction acts like a brake on Earth's rotation. Every tide that rises and falls on our shores is stealing a tiny amount of rotational energy from Earth, transferring it to the Moon's orbit. It's a trade, often written into the laws of celestial mechanics. Earth spins slower, and the Moon gradually moves farther away. The beauty of exploring this gradual change is that it allows us to contemplate transformation without anxiety. We're not imagining disaster. We're imagining evolution, planetary evolution, happening at nature's own unhurried pace. We can watch ecosystems adapt slowly over millions of years. We can see civilizations adjust their rhythms gradually, generation by generation. We can witness the patient reorganization of atmospheric patterns, ocean currents, climate zones, all unfolding like a flower opening, slow enough that each stage blends seamlessly into the next. Let yourself relax into this timescale. Let go of the human perspective where change happens quickly, where years matter, where we measure time in lifetimes. Adopt instead the perspective of planets, where 1,000,000 years is brief, where continents drift and mountains rise and fall, where species evolve and go extinct in what amounts to geological moments. From this perspective, Earth's rotation slowing is not frightening. It's simply another chapter in the planet's long story. Picture Earth from space, that beautiful blue marble suspended in the void, rotating peacefully. Watch it spin, one rotation taking 24 hours, the terminator line between day and night creeping steadily westward, sunrise following sunrise around the globe in an endless wave. This is the Earth, you know. The Earth, whose rotation has remained essentially constant throughout all of human history, throughout the rise and fall of every civilization, throughout the entire existence of our species. Now imagine that rotation slowing. Not stopping, not yet, just slowing. The change is so gradual that if you were standing on the surface, you'd never notice. The sun would still rise in the east, still set in the west. Days would still follow nights. But over centuries, subtle differences would accumulate. Astronomers would notice first, their precise measurements showing that days are getting longer. Atomic clocks, accurate to billionths of a second, would reveal the change. But in everyday life, nothing would seem different. This is how planetary transformations happen in reality, not in dramatic catastrophes, but in slow accumulations of tiny changes. The same way the Himalayas rose, millimeter by millimeter, pushed up by the patient collision of tectonic plates over tens of millions of years. The same way the Grand Canyon formed, grain by grain, carved by the Colorado River over 6 million years. The same way species evolve, generation by generation, mutation by mutation, across millions of years of natural selection. We're going to follow this process together, watching Earth's rotation slow from its current comfortable 24-hour day through increasingly longer cycles, all the way to its ultimate destination billions of years in the future tidal lock, where Earth shows the same face to the sun always, where one hemisphere experiences eternal day and the other eternal night, but we'll take our time getting there. We'll pause at each stage, examining what life would be like, how the planet would change, what the sky would look like, how the oceans would behave. We'll explore the science calmly and thoroughly, understanding the physics without urgency, appreciating the elegant inevitability of gravitational mechanics. There's something deeply soothing about contemplating such vast timescales. When you think in billions of years, human concerns become beautifully small. The stresses of tomorrow, the worries of next week, they dissolve against the backdrop of deep time. We become like mayflies contemplating glaciers, our brief lives flickering against the slow patience of planetary evolution. So settle in now. Breathe slowly. Let your body relax completely. We're going to journey through time together, watching Earth's rotation slow across millions and billions of years. We'll witness changes that no human will ever actually see, explore possibilities that exist only in thought experiments and computer models. Contemplate a future so distant that the sun itself will have changed before Earth achieves its final rotational state. This is a journey of imagination grounded in physics, of speculation built on solid science, of wonder tempered by understanding. Let the patient pace of planetary evolution carry you into relaxation, into peace, into the gentle drift toward sleep. The story we're about to tell unfolds over timescales so vast that thinking about them naturally slows your mind, quiets your thoughts, prepares you for rest. Earth spins beneath you right now at over 1,000 miles per hour at the equator, and you feel nothing, just gentle, stable normalcy. This rotation has been your constant companion, since before you were born, will remain essentially unchanged throughout your entire life. You are safe here, on this spinning world, protected by the stability of planetary motion that has persisted for billions of years and will persist for billions more. Rest now in that safety. Let the thought of Earth's patient, gradual transformation soothe you. We're about to explore what would happen if the spin slowed, but we'll do it together, calmly, with the unhurried pace that such a planetary change deserves. Before we begin slowing Earth's rotation in our imagination, let's first appreciate what we have right now, the perfect spin, the ideal day-night cycle, the rotation that makes life as you know it possible. Earth rotates once every 23 hours, 56 minutes, and 4 seconds. You might be surprised it's not exactly 24 hours. That's a common misconception. A full rotation relative to the distant stars, what astronomers call a sidereal day, takes 23 hours and 56 minutes. The 24-hour day we use, the solar day, is slightly longer because Earth is also orbiting the Sun. Each day, Earth moves a bit along its orbital path, so it has to rotate slightly more than one full turn to bring the Sun back to the same position in the sky. This distinction is subtle, beautiful in its precision, a reminder that even something as familiar as the length of a day involves elegant astronomical geometry. The ancient astronomers who discovered this, who noticed that the stars rise 4 minutes earlier each night, slowly cycling through the seasons, were uncovering deep truths about Earth's motion through space. At the equator, Earth's surface is moving at approximately 1040 miles per hour. Think about that for a moment. Right now, as you lie still, you're hurtling through space at over 1,000 miles per hour, spinning with the planet. At mid-latitudes, say, around 40 degrees north or south, the speed drops to about 800 miles per hour. At the poles, the rotational velocity is nearly zero. You'd simply rotate in place, completing one turn every 24 hours like a slow pirouette, yet you feel none of this motion. The air moves with you. The ground beneath you moves with you. Everything in your immediate environment shares this velocity perfectly, so there's no sensation of movement at all. It's only when you look at celestial objects, the sun rising and setting, the moon crossing the sky, the stars wheeling overhead, that you see evidence of this rotation. This is one of the beautiful insights of physics. Constant velocity motion is indistinguishable from being at rest. Galileo understood this 400 years ago. Einstein built his theory of relativity on this principle. You could be in a perfectly smooth train moving at constant speed with the curtains drawn, and you'd have no way to know you were moving. Earth is like that train, moving at tremendous speed, but so smoothly, so constantly, that the motion becomes invisible. The rotation creates a subtle but important force, the Coriolis effect. Because different latitudes move at different speeds, objects moving north or south appear to curve. This deflection shapes our weather. It's why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's why winds don't blow directly from high pressure to low pressure, but curve as they flow. It's why ocean currents form vast gyres, circular patterns hundreds or thousands of miles across. Artillery officers must account for the Coriolis effect when firing long-range guns. A shell traveling 30 kilometers takes time to reach its target, and during that time, the target has moved because Earth has rotated beneath the shell's flight path. For truly long-range shots, ignoring this effect means missing by hundreds of meters. Even something as seemingly simple as dropping an object from a tall tower is affected. Though the deflection is tiny, only a few millimeters for a tower 100 meters tall, falling objects land slightly to the east of a point directly below their release point, because Earth's surface moves eastward during their fall. The rotation also creates a bulge at Earth's equator. Centrifugal force, the outward force you feel when spinning, pushes material at the equator outward, making Earth slightly oblate, meaning wider at the equator than from pole to pole. The difference is small. Earth's equatorial diameter is 43 kilometers greater than its polar diameter, less than 1%, but it's measurable, real, a permanent deformation of the planet caused by its spin, This bulge has consequences. It affects satellite orbits. It contributes to the precession of Earth's axis, the slow wobble that takes 26,000 years to complete a cycle. It makes gravity slightly weaker at the equator than at the poles, both because you're farther from Earth's center and because the centrifugal force partially opposes gravity. If you weigh 200 pounds at the North Pole, you'd weigh about 199 pounds at the equator, a small difference, but real. Day and night, the most fundamental rhythm of life on Earth, exist because of this rotation. Every organism has evolved in the context of this 24-hour cycle. Plants open their flowers at specific times of day, close them at night. Animals are diurnal or nocturnal, active when light or darkness suits their survival strategy. Humans have circadian rhythms, internal biological clocks that regulate sleep, hormone production, body temperature, countless physiological processes on a roughly 24-hour cycle. These circadian rhythms are so fundamental that they persist even without external cues. If you lived in a cave with no access to sunlight, no clock, no way to know what time it was, your body would still maintain a roughly 24-hour cycle. You'd still feel sleepy at regular intervals, still wake up after sleeping, still experience the rise and fall of body temperature and hormone levels that mark biological day and night. Your internal clock might drift slightly. Most people's natural circadian period is slightly longer than 24 hours, closer to 24 and a half. But it would remain remarkably close to Earth's rotation period. This is not coincidence. This is billions of years of evolution fine-tuning organisms to Earth's rotation. Life has adapted so completely to the 24-hour day that it's built into our DNA, into the cellular mechanisms that regulate when genes turn on and off, into the neural circuits that control our behavior. The rotation also drives atmospheric circulation in ways that create the climates we depend on. Warm air rises at the equator, where solar heating is strongest. This air flows toward the poles at high altitude, cooling as it goes, eventually sinking back to the surface at mid-latitudes and flowing back toward the equator. But Earth's rotation disrupts this simple pattern, creating three circulation cells in each hemisphere: the Hadley cell in the tropics, the Ferrel cell in mid-latitudes, the polar cell in high latitudes. These circulation patterns create the trade winds that guided sailing ships across the oceans, the westerlies that bring weather systems across North America and Europe, the polar easterlies that circle Antarctica. Without this rotation, atmospheric circulation would be completely different. We'd have simple north-south flow, one giant convection cell in each hemisphere. The climate patterns we know, the wet tropics, the dry subtropics, the temperate mid-latitudes, the cold poles, would reorganize entirely. Ocean currents, too, depend on Earth's rotation. The great conveyor belt of thermohaline circulation, warm surface water flowing from the tropics toward the poles, cooling and sinking, cold deep water flowing back toward the equator, is shaped by rotation. Surface currents like the Gulf Stream carry warm water northeast across the Atlantic, warming Europe far beyond what its latitude would suggest. The Kuroshio current does the same for East Asia. These currents exist because of the complex interaction between wind, water density differences, and the Coriolis effect from Earth's rotation. Think about how perfectly balanced everything is right now. The 24-hour day is long enough that day and night temperatures don't vary too wildly. The sun is up long enough to warm the surface, but not so long that one side becomes scorching while the other freezes. Short enough that diurnal organisms can sleep through the night without starving. but long enough that nocturnal organisms have plenty of darkness to hunt and forage. The rotation speed creates weather patterns vigorous enough to distribute heat and moisture around the planet, preventing extreme temperature gradients, but not so vigorous that storms become unmanageable. It generates a magnetic field through dynamo action in Earth's molten outer core. The rotation of electrically conductive liquid iron creates electric currents, which generate magnetic fields, which interact with the flow to sustain themselves in a self-perpetuating cycle. This magnetic field deflects harmful solar wind, protecting our atmosphere from being stripped away into space. Everything about Earth's current rotation seems almost deliberately calibrated for habitability. This is, of course, an illusion, life adapted to the rotation we have, not the other way around. But the match is so precise, so perfect, that it's worth pausing to appreciate before we begin our thought experiment of slowing it down. Right now, at this very moment, you're experiencing the result of 4-5 billion years of planetary evolution. Earth's rotation has slowed considerably since the planet formed. Days were only 5 or 6 hours long just after the moon formed from the Theia impact, but the slowdown has been gradual enough that life has continuously adapted, species evolving to match whatever day length existed during their time. You are alive at a moment when the day is 24 hours long, when this duration has been stable for millions of years, when it will remain stable for millions more. This is your normal, your baseline. The rhythm that feels natural and right, because it's the only rhythm you've ever known. Breathe slowly now, in rhythm with this rotation. Feel yourself turning with the planet, moving through space at 1,000 miles per hour, yet feeling perfectly still. Appreciate the delicate balance, the perfect calibration, the gentle predictability of day following day in an endless, reliable cycle. This is what we're about to change in our imagination. This perfect rotation will slow, but we'll do it gradually, patiently, watching carefully what happens at each stage. And by understanding what we might lose, we'll appreciate even more what we have right now. This beautiful, perfect 24-hour spin that makes our world habitable, our lives possible, our existence secure. Rest in that security now. Let the stability of Earth's rotation comfort your head, prepare you for the journey. Now let's understand how Earth's rotation actually slows, the mechanism behind this gradual deceleration, the elegant physics that governs the transfer of energy between our planet and its moon. This is not speculation or fantasy. This is happening right now, has been happening for billions of years, and will continue for billions more. It's one of the most beautiful examples of gravitational mechanics in our solar system, and understanding it helps us appreciate the deep interconnection between Earth and Moon. The process is called tidal braking, or tidal friction, and it begins with something you've seen countless times: ocean tides. Picture the moon in orbit around Earth. The moon's gravity pulls on everything on our planet, but it pulls harder on the side facing the moon than on Earth's center, and harder on Earth's center than on the far side. This difference in gravitational force, this gradient, is what we call a tidal force. It doesn't pull Earth uniformly but stretches it, elongating the planet slightly along the Earth-Moon line. Water, being fluid, responds most dramatically to this stretching. The oceans bulge outward on the side facing the moon and, somewhat less intuitively, on the opposite side as well. The far side bulge occurs because Earth's center is pulled away from the water on that side, leaving it behind. The result is two bulges, tidal bulges, one facing the moon and one facing away. If Earth didn't rotate, these bulges would remain perfectly aligned with the moon. The moon would pull on them, they'd pull back, and everything would be in equilibrium. No energy transferred, no rotation change, just a stable configuration. But Earth does rotate. Earth rotates much faster than the moon orbits, one rotation every 24 hours versus the moon's 27-day orbital period. This rotation carries the tidal bulges forward, ahead of the Earth-Moon line. The bulges try to stay aligned with the moon, but Earth's rotation drags them eastward, creating a misalignment. Imagine watching from space above the North Pole. Earth rotates counterclockwise. The moon orbits counterclockwise. But Earth spins much faster, so the tidal bulges, which try to point toward the moon, get carried ahead by Earth's rotation. The bulge that should point directly at the moon instead points slightly ahead of the moon's position. This misalignment is crucial. Now the moon's gravity pulls on bulges that aren't aligned with it. The moon pulls backward on the leading bulge, trying to slow Earth's rotation. Simultaneously, Earth pulls forward on the moon through this misaligned bulge, trying to speed up the moon's orbit. It's a gravitational tug of war, with rotational energy being transferred from Earth's spin to the moon's orbit. The mathematics are elegant. Angular momentum must be conserved in the Earth-Moon system. When Earth loses rotational angular momentum, that momentum must go somewhere. It goes into the moon's orbit. The moon gains orbital angular momentum, which means it moves into a higher orbit, farther from Earth. Meanwhile, Earth's rotation slows. This is actually observable. Laser ranging experiments, where scientists bounce laser beams off mirrors left on the moon by Apollo astronauts, measure the Earth-Moon distance with incredible precision. These measurements show that the moon is receding from Earth at about 3.8 centimeters per year. Nearly 4 centimeters annually, year after year, the moon drifts farther away. Simultaneously, Earth's day is lengthening. Precise astronomical observations, combined with ancient eclipse records and geological data, show that Earth's day increases by about 1.7 milliseconds per century. This seems infinitesimal. You could never perceive such a tiny change, but over geological time, it accumulates into something substantial. Let's do the math to appreciate the timescale. At 1.7 milliseconds per century, it takes about 60,000 years for the day to lengthen by 1 second. To add an entire hour, 600 seconds, would take over 200 million years. To double the day length from 24 hours to 48 hours would take roughly 5 billion years at the current rate. But here's an important subtlety: the rate isn't constant. Tidal breaking depends on the distance between Earth and Moon. The closer they are, the stronger the tidal forces, the faster the energy transfer. As the Moon moves farther away, the tidal forces weaken, and the breaking slows down. Early in Earth's history, when the Moon was much closer, perhaps only 30,000 kilometers away compared to today's 384,000 kilometers, tidal breaking was much more vigorous. Days lengthened more rapidly then. We can see evidence of this in the geological record. Coral fossils from the Devonian period, about 400 million years ago, show daily growth rings much like tree rings show annual growth. By counting these rings between seasonal markers, paleontologists determined that Devonian days were about 21.8 hours long. The year still had the same length. Earth's orbit around the Sun hasn't changed significantly, but it contained about 400 days instead of today's 365. Going back farther, to 900 million years ago during the Neoproterozoic era, geological evidence suggests days were only about 18 hours long. And shortly after the Moon's formation 4.5 billion years ago, when the Moon was much closer and Earth had just finished coalescing from the debris of the Theia impact, Days were only 5 to 6 hours long. Earth spun rapidly, a full rotation in less time than your typical workday, completing 4 rotations in what we'd now call a single day. The moon, correspondingly, was much closer, perhaps only 15,000 to 20,000 kilometers away, compared to 384,000 kilometers today. It would have appeared enormous in the sky, perhaps 20 times larger in angular diameter than the moon you see now. Tides would have been catastrophically high, raising ocean levels by hundreds of meters, creating incredible tidal bores as water rushed around the rapidly rotating planet. But tidal braking operated then as it does now, gradually, persistently, transferring energy. The moon drifted outward. Earth's spin slowed. The process has been continuous for 4-5 billion years and will continue for billions more. There's a fascinating end state to this process, at least theoretically. If the Earth-Moon system existed in isolation for long enough, tidal braking would eventually bring them into mutual tidal lock. Earth would rotate once per lunar orbit, always showing the same face to the moon, just as the moon already shows the same face to Earth. At that point, the tidal bulges would be perfectly aligned with the moon, no longer misaligned by rotation, and the energy transfer would cease. Earth's rotation would stabilize, and the moon's orbital distance would stabilize. But this endpoint will never actually be reached. The timescale required is roughly 50 billion years, and the sun will end its main sequence lifetime in only 5 billion years, becoming a red giant and likely engulfing both Earth and Moon long before mutual tidal lock could occur. So Earth's rotation will continue slowing for the next few billion years, but the story will end differently, probably with Earth being vaporized by an expanding sun, rather than achieving perfect tidal synchronization with the Moon. Still, understanding this mechanism helps us appreciate the deep connection between Earth and Moon. The Moon's presence isn't just about providing light at night or creating poetry, inspiring crescents and full moons. The Moon is actively shaping Earth's rotation, has been shaping it for billions of years, gradually slowing our spin through the patient, inexorable mechanics of tidal friction. Every high tide, every low tide, every ebb and flow of ocean water is part of this grand exchange of energy. The tides you see at the beach aren't just water sloshing around. They're the visible manifestation of gravitational forces, transferring rotational energy from Earth to the Moon's orbit, gradually transforming our planet's spin rate over billions of years. There's something profoundly soothing about understanding this process. It's not random. It's not chaotic. It's governed by precise physical laws, by conservation of angular momentum, by gravitational mechanics that we understand thoroughly. The change is gradual, predictable, calculable. We can measure it happening in real time with laser ranging. We can see its effects in ancient fossils. We can project it into the future with confidence. This is nature operating on its longest timescales, making changes so slowly that they're imperceptible to individual organisms, but profound over geological epochs. It's the same patient pace that builds mountains through tectonic collisions, carves canyons through river erosion, shapes coastlines through wave action. Nature isn't hurried. Nature takes its time. Rest now in that understanding. Feel the gentle pull of the moon overhead, whether it's visible in your sky or on the opposite side of the planet. That moon is connected to you through gravity, through tides, through the slow transfer of rotational energy that has been ongoing since before life existed on Earth. The same forces that slow Earth's rotation are operating right now, this very moment, as they have every moment for billions of years. The tides rise and fall. The moon drifts slowly outward. Earth's rotation gradually slows. All of it precise, predictable, patient. All of it part of the grand choreography of celestial mechanics. The beautiful physics that governs the motions of worlds. Let that understanding settle over you like a blanket. The universe operates according to laws, follows patterns, exhibits regularities that we can comprehend and predict. Earth's rotation slowing isn't mysterious or frightening. It's just physics, operating exactly as it should, at exactly the pace it should, governed by principles as reliable as mathematics itself. Breathe slowly. Feel yourself part of this vast system. Earth rotating beneath you, moon orbiting above, tidal forces exchanging energy between them, all of it unfolding at nature's patient, unhurried pace. Let the deep time perspective calm your mind, prepare you for the journey ahead as we explore what happens when this process continues into the distant future. To truly appreciate Earth's changing rotation, we need to look backward through time, tracing the lengthening of days from the planet's violent birth to the comfortable 24-hour rhythm we know today. This journey through deep time reveals not just numbers and measurements, but a story of planetary evolution, of gradual transformation, of nature patiently reshaping the fundamental rhythms of our world. Let's begin at the very beginning. 4.5 billion years ago, in the immediate aftermath of the Theia impact, that tremendous collision between Proto-Earth and a Mars-sized body that created our moon and fundamentally reshaped our planet. In those earliest days, just after the moon coalesced from the debris disk orbiting the newly merged Earth, Theia, our planet spun with extraordinary speed. A complete rotation took only 5 to 6 hours. Imagine that for a moment, sunrise to sunset in just 2.5 to 3 hours. Darkness to dawn in the same brief span. A full day, night cycle completed faster than your typical afternoon. The moon, newly formed and still glowing with the heat of its creation, hung enormous in the sky. It orbited at perhaps only 15,000 to 20,000 kilometers from Earth's surface, less than 1/20th of today's distance. From Earth's surface, the moon would have appeared gigantic, subtending an angle perhaps 20 times larger than the moon you see today. It would have dominated the sky, a vast sphere of molten rock slowly cooling, its surface visibly churning with volcanic activity, glowing dull red in the darkness. The tides in this configuration would have been catastrophic by modern standards. With the moon so close and Earth spinning so rapidly, ocean tides might have risen hundreds of meters, perhaps even a kilometer or more, creating enormous bores of water that rushed around the planet. Of course, Earth's surface was still largely molten at this point, so ocean tides is perhaps misleading. These were tides in the magma ocean that covered much of the surface, bulges of molten rock responding to the moon's powerful gravitational pull. The intense tidal forces generated tremendous friction, both in whatever water existed and in Earth's solid body. Yes, even solid rock experiences tidal deformation, though much less dramatically than water. This friction extracted rotational energy at a prodigious rate. Earth's spin slowed rapidly in those early eons, and the moon receded correspondingly quickly. Move forward now to about 4 billion years ago, perhaps 500 million years after Earth's formation. The planet has cooled considerably. A solid crust has formed. The great rain has fallen, creating the first stable oceans. Life may be beginning in those primordial seas, though evidence is scarce and controversial. And Earth's day has already lengthened significantly, perhaps to 8 or 10 hours now. Still far shorter than today, but considerably longer than those first frantic rotations just after the moon's birth. The moon has receded to perhaps 50,000 or 60,000 kilometers. Still much closer than today, still appearing several times larger in the sky, but no longer the overwhelming presence it was in those earliest days. Tides remain vigorous but no longer world-shaking. The tidal friction continues its patient work, slowing Earth's rotation, pushing the moon outward, operating on timescales of millions and billions of years. Jump forward another billion years to 3 billion years ago. Earth is now middle, aged by cosmic standards, though still young by biological ones. Bacterial life has definitely taken hold, forming stromatolites, layered microbial mats, in shallow seas. Photosynthesis has begun, though oxygen remains scarce in the atmosphere, and the day length has continued its inexorable increase, perhaps reaching 12 to 14 hours now. This is still remarkably short by our standards. The sun would race across the sky, rising to noon to setting in just 6 or 7 hours. Darkness would last an equivalent time. Any organism with circadian rhythms would have synchronized to this rapid cycle, their internal clocks ticking twice as fast as ours, adapted to a world that spun nearly twice as quickly, now advanced to 5 billion years ago, to the beginning of the Great Oxidation Event, when photosynthetic bacteria began releasing oxygen as a waste product in sufficient quantities to fundamentally change Earth's atmosphere. Days might be 15 or 16 hours long now. The moon continues its slow recession, now perhaps at 200,000 kilometers distance, still closer than today, but approaching something more familiar. Fast forward again to 900 million years ago, during the Neoproterozoic era. This is an important time marker because we have geological evidence, rhythmites, sedimentary layers deposited by tidal action, that allow us to calculate day length with reasonable precision. Analysis of these rhythmites suggests that days were approximately 18 hours long. The year still contained the same number of Earth orbits around the Sun, but that year was divided into about 486 days rather than today's 365. Think about what this means. If you could travel back to this time and live for one of our current years, you would experience 486 sunrises and sunsets instead of 365. Each individual day would feel rushed by our standards. 9 hours of daylight, 9 hours of darkness, a full cycle completing in 3/4 of what we consider a day. But to organisms living then, this was normal, natural, the only rhythm they'd ever known. The geological record from this period is fascinating. Tidal rhythmites, thin layers of sediment deposited by tides, show clear patterns of spring tides and neap tides. By counting the layers between spring tides, geologists can determine how many days occurred in a lunar month. Combined with knowledge of how many lunar months occurred in a year, this gives us the day length. It's detective work on a geological scale, reading Earth's ancient rhythms preserved in stone. Move forward again to 620 million years ago, to the Ediacaran period just before the Cambrian explosion of complex life. Days were perhaps 19 hours long now. Strange, soft-bodied organisms, the Ediacaran biota, lived in shallow seas, forms unlike anything alive today, possibly early experiments in multicellular life that left no descendants. They lived their lives under a day-night cycle still noticeably shorter than ours, though approaching modern length. Then comes the Cambrian explosion, 540 million years ago, when complex life diversified dramatically, filling the oceans with trilobites, early fish, strange arthropods, and countless other forms. Day length was perhaps 20 to 21 hours. The lengthening continues, but the rate has slowed. With the moon now farther away, tidal forces are weaker. Energy transfer less vigorous. The process continues but more gradually than in Earth's youth. By 400 million years ago, During the Devonian period, the age of fishes, when plants were just beginning to colonize land, we have excellent evidence from coral fossils. Corals grow in daily rhythms, adding tiny layers of calcium carbonate each day. They also show seasonal variations, growing faster in summer than winter. By examining Devonian coral fossils and counting the daily growth lines between seasonal bands, paleontologists determined that Devonian days were about 21.8 hours long and the year contained approximately 400 days. This is remarkably close to modern-day length, less than 10% shorter. The rapid changes of Earth's youth have given way to a much more gradual evolution. Still, the difference is perceptible. If you could experience a Devonian day, you'd notice the faster pace, sunrise coming a couple hours earlier than you expect, sunset arriving sooner, the full cycle completing before you quite feel ready for it. Move forward through the Carboniferous period 300 million years ago, when vast swamp forests would eventually become coal deposits, through the Permian, when the supercontinent Pangaea dominated the globe, through the Triassic and the rise of dinosaurs. Days continue lengthening, approaching 23 hours by the time dinosaurs reach their peak in the Jurassic and Cretaceous periods. The dinosaurs lived their entire existence, over 160 million years of dominance, under day lengths very close to what we experience today. A Tyrannosaurus rex experienced nearly the same 24-hour day-night cycle that you do. The asteroid impact that ended their reign 66 million years ago occurred during a day perhaps just 20 or 30 minutes shorter than today's. And from that extinction forward, through the rise of mammals, through the evolution of primates, through the emergence of humans, day length has remained essentially stable at 24 hours. All of human evolution, from our earliest ancestors to modern Homo sapiens, has occurred under this same day-night rhythm. Our circadian clocks evolved to match it, our sleep cycles synchronized to it. Our entire biology is calibrated to Earth's current rotation rate. Looking at this vast sweep of time, 4-5 billion years compressed into a few paragraphs, reveals the pattern clearly. Rapid change early on when the moon was close and tidal forces strong. Gradual slowing of the change rate as the moon receded and tidal friction weakened. Arrival at a relatively stable day length that has persisted for hundreds of millions of years, and will persist for hundreds of millions more. This perspective is deeply comforting. Yes, Earth's rotation is slowing, but the change is so gradual that it's essentially imperceptible on human timescales. Days have been 24 hours long throughout all of human history, and will remain 24 hours long for millions of years into the future. The stability we feel, the regularity of day following day, is real and enduring. The ancient organisms that lived under shorter days adapted perfectly to those rhythms. Life evolves to match planetary conditions, whatever those conditions might be. If days continue to lengthen in the far future, life will adapt to that as well, generation by generation, evolving new circadian rhythms to match the changing cycle. There's a profound lesson here about adaptation and timescales. Change that seems dramatic when compressed into a paragraph, days going from 6 hours to 24 hours, is actually glacially slow when experienced in real time. No organism ever noticed days getting longer. No dinosaur woke up confused because sunrise came later. The change is too slow, spread across too many generations, for individual experience to detect. This is how planetary evolution works. This is the pace of astronomical change. Not sudden, not dramatic, but patient, gradual, operating on timescales that dwarf civilizations and species. Understanding this helps us appreciate both the stability of our current conditions and the inevitability of very slow, very gradual change. Rest now in this deep time perspective. Let your mind drift back through the eons, through Devonian seas and Carboniferous forests, through the age of dinosaurs and the rise of mammals, through the emergence of your own species. All of it unfolding under gradually lengthening days, all of it adapting and evolving to match Earth's slowly changing rotation. You are part of this long story, this 4-5 billion year journey from a rapidly spinning world to the stable, comfortable rotation you experience today. Let that continuity connect you to deep time, to the patient processes that shape planets and evolve life. Let it calm you, ground you, prepare you for seated in a gentle embrace of Earth's ancient, slowly changing spin. Now let's step into our thought experiment properly, imagining Earth's rotation beginning to slow more rapidly than it naturally would. Not catastrophically, remember. We're maintaining the calm, gradual approach, but noticeably, measurably, over the course of centuries rather than billions of years. We'll begin with the earliest phase, when days have lengthened from 24 hours to 25, then 26, gradually creeping longer as Earth's spin decelerates. Picture yourself living through this early transition. You're born into a world where the day is still essentially 24 hours long, perhaps 24 hours and 10 minutes, a difference too small to notice in daily life. But as you age, the lengthening becomes measurable. By the time you're middle-aged, days are 24 hours and 45 minutes. By the time you're elderly, they've reached 25 hours and 15 minutes. Still close to what you've always known, but subtly, persistently different. The first people to notice would be astronomers and timekeepers. Atomic clocks, precise to billionths of a second, would register the discrepancy immediately. The Earth's rotation, traditionally used to define our basic time unit, would be falling out of sync with atomic time. Scientists would issue regular bulletins about the lengthening day, adding leap seconds more and more frequently to keep civil time aligned with Earth's rotation. But for most people, daily life would continue essentially unchanged for quite some time. Your alarm clock still rings at what you call 7000 AM, though 7000 AM is becoming an increasingly arbitrary designation. The sun still rises in the east, still sets in the west. Your commute takes the same amount of time. Your workday feels the same length. The changes are too gradual for human perception to register directly. However, sensitive instruments and carefully designed experiments would reveal the truth. Foucault pendulums, long pendulums whose plane of oscillation rotates as Earth spins beneath them, would complete their rotations more slowly. The Coriolis effect, which deflects moving objects due to Earth's rotation, would weaken slightly. Long-range artillery calculations would need adjustment. Satellite orbits, carefully designed based on Earth's rotation rate, would need correction. Biologists would begin noticing effects in organisms with precise circadian rhythms. Most living things have internal biological clocks that regulate daily cycles of activity and rest, synchronized to Earth's 24-hour day. These clocks aren't infinitely flexible. They can adjust to small variations. This is why you can gradually adapt to a new time zone when traveling. But they function best when external day length closely matches their internal period. In humans, the circadian pacemaker in the brain, a cluster of neurons in the hypothalamus, called the suprachiasmatic nucleus, maintains a rhythm of approximately 2 hours when isolated from external cues. Natural daylight exposure normally entrains this slightly longer internal rhythm to Earth's exactly 24-hour day. With days now at 24, 5 or 25 hours, the match would actually improve slightly for some people. Those with naturally longer circadian periods might find themselves sleeping better, feeling more alert, their internal clocks aligning more comfortably with the external world, but others, particularly those with shorter natural circadian periods around 23.8 hours, would struggle. They'd experience something like permanent jet lag, a persistent mismatch between their internal clock and the external day-night cycle. Sleep disorders might become more common. People would compensate with artificial lighting, blackout curtains, carefully timed exposure to bright light to shift their internal rhythms. But some would always feel slightly out of sync. Animals would face similar challenges. Diurnal species, those active during daylight, have evolved circadian rhythms matched to roughly 12 hours of light and 12 hours of darkness. With days now stretching to 25 hours, they'd experience 12.5 hours of light and 12.5 hours of darkness. For most species, this half-hour extension wouldn't be catastrophic, but it would require adjustment. Birds that navigate by sun position would need to recalibrate their internal sun compass. Many bird species use the sun's position, combined with an internal clock, to determine direction during migration. With the sun moving more slowly across the sky, taking 25 hours to complete its circuit rather than 24, their calculations would be off unless they adjusted their internal timing mechanisms. Nocturnal animals, bats, owls, many rodents, face different challenges. They've evolved to compress their active period into the hours of darkness, and many can't function well in daylight due to eye sensitivity or vulnerability to predators. An extra hour of darkness per night might seem like a benefit, but it disrupts the precise timing that governs their behavior. Owls hunting by sound in darkness have learned to predict exactly when prey species will be most active. Shifting that schedule by even an hour creates mismatches. Plants would experience the change differently. Photosynthesis depends on light availability, and most plants have evolved to maximize light capture during the day, while conducting different metabolic processes at night. An extra hour of daylight means an extra hour of photosynthesis, which sounds beneficial, more energy captured, more growth potential. But plants also depend on darkness for certain processes. Many flowering plants use night length as a cue for when to bloom. Short day plants flower when nights exceed a certain length. Long day plants when nights are shorter than a threshold. These photoperiod responses are how plants track seasons, ensuring they flower at optimal times for pollination and seed development. With night length changing, these cues become unreliable. Spring, blooming plants might flower at the wrong time, missing their pollinators. Agricultural crops bred for specific day lengths might fail to flower properly. The lengthening day would also affect temperature patterns, though subtly at first. Currently, temperatures peak in mid-afternoon, a few hours after solar noon, as the ground continues absorbing heat, even as the sun starts its descent. Overnight, the ground radiates heat away, reaching minimum temperature just before dawn. With a 25-hour day, this rhythm stretches. Afternoons might get slightly warmer as the sun stays up longer, allowing an extra hour of heating. Nights might get slightly cooler, as the extended darkness allows more heat loss. The difference would be small in this early phase, perhaps a degree or 2 Celsius change in daily temperature range, but it would affect ecosystems already stressed by climate change. Desert organisms living at the edge of heat tolerance might find the extra afternoon heating pushes them beyond survival limits. Arctic species might benefit from cooler nights during summer. When darkness returns, or suffer from extended daylight heating during the polar summer, when the sun barely sets anyway. Weather patterns would begin shifting subtly. The general circulation of the atmosphere, the Hadley cells in the tropics, Ferrel cells in mid-latitudes, polar cells in high latitudes, depends on Earth's rotation rate. The Coriolis effect, which helps organize these circulation patterns, weakens as rotation slows. At 25-hour days, the change would be minor, perhaps a few percent weaker than current, but meteorologists would detect it in long-term weather statistics. Hurricanes might become slightly less organized. These massive storms depend on the Coriolis effect to maintain their rotation and structure. A weaker Coriolis effect means hurricanes might not intensify as readily, or might dissipate more quickly. This could actually reduce hurricane damage in some regions, though the relationship between rotation rate and storm intensity is complex and not entirely predictable. Ocean currents would experience subtle changes. The great gyres, the circular current systems in each ocean basin, are driven partly by wind and partly by the Coriolis effect. Slower rotation means weaker Coriolis deflection, which could gradually alter current paths. The Gulf Stream might shift slightly. The Kuroshio current could change its northward reach. These changes would be minimal at first, but they'd be the beginning of a larger reorganization that would become more pronounced as rotation continued slowing. Human civilization would adapt relatively easily to 25-hour days. We're remarkably flexible as a species, and a 1-hour change is well within our adaptive capacity. Work schedules would gradually shift. Instead of an 8-hour workday in a 24-hour day, perhaps we'd move to an 8.5-hour workday in a 25-hour day, maintaining roughly the same proportion of work to rest. Television programming would adjust, spreading shows across the longer day. Airlines would recalculate flight schedules. Schools might start slightly later and end slightly later, maintaining the same instructional hours, but distributed across the longer day. Sports leagues would continue playing games, though night games might start a bit later to ensure darkness. The calendar would require attention. Our current calendar is built around 24-hour days, 365 of them in a normal year, 366 in leap years. With 25-hour days, we'd face a choice: keep the calendar year at 365 days and accept that it no longer quite matches Earth's orbit, or adjust the calendar to maintain alignment with the seasons. Likely we'd adjust, perhaps moving to a 350-day calendar year or introducing more complex leap year rules to maintain synchronization. Agriculture would adapt more slowly, but eventually successfully. Farmers would experiment with planting times and crop varieties to match the new day length. Greenhouses could maintain artificial 24-hour cycles if desired, shielding plants from the changing external rhythm. Livestock, particularly chickens whose egg-laying depends on day length, might be housed in controlled environments to maintain productivity. In this early phase, the dominant emotional tone would be adjustment rather than crisis. Yes, things are changing, but gradually, manageably. Every generation would grow up with days slightly longer than their parents experienced, and to them it would feel normal. The 25-hour day would become the new baseline, the new normal, what everyone expects and plans around. There would be nostalgia, certainly. Older people would remember when days were shorter, when the rhythm felt different. There would be cultural works, books, films, songs, exploring the meaning of changing day length, what it says about human adaptability, whether we're losing something essential as the familiar 24-hour cycle slips away, but life would continue. People would still wake up, Go to work, eat meals, spend time with family, pursue hobbies, fall asleep at night. The fundamental patterns of human existence don't depend critically on whether a day is 24 or 25 hours long. We'd adapt, adjust, carry on. And all the while, Earth would continue its gradual deceleration. The 25-hour day wouldn't be an endpoint, but just a milestone, a way marker on the longer journey toward even slower rotation. Days would continue lengthening, 26 hours, 27, 30, beyond, each change requiring new adaptations, but each change happening slowly enough that life could adjust. Rest now in this vision of gradual change. Feel how humans and nature can adapt to shifting conditions when those shifts happen slowly, predictably, giving time for adjustment. There's no catastrophe here, no sudden disaster, just the patient unfolding of planetary change, and the equally patient adaptation of life to match those changes. Let this understanding settle over you. Change is inevitable, but slow change allows adaptation. Evolution operates on exactly this principle. Gradual environmental shifts favoring those organisms best suited to new conditions, generation by generation, until entire ecosystems have transformed to match their changed world. Breathe slowly, matching your breath to this patient pace of change. Feel yourself relaxing into the understanding that transformation doesn't have to be traumatic, that given enough time, life finds ways to adapt, to persist, to thrive under new conditions. Let this knowledge ease you toward sleep, toward rest, toward the peaceful acceptance of change as natural and survivable. We're going to accelerate now through the passage of time, watching as Earth's rotation continues its gradual decline. Days have lengthened from 25 hours to 30, then 35, then 40. We arrive now at a significant threshold, the 50-hour day. A day-night cycle that spans more than 2 of our current days. This is where the changes become unmistakable, where adaptation requires more than minor adjustments, where the world begins to feel genuinely different from what humanity has known throughout its entire existence. Picture waking up in this world. You open your eyes after a full night's sleep, perhaps 8 or 9 hours. Your circadian rhythm having stretched somewhat to accommodate the longer cycle, though not proportionally. The sun rose about 12 hours ago. It's currently what we might call mid-afternoon in the old 24-hour framework, but in this 50-hour day, the sun still has another 13 hours before it sets. 25 hours of continuous daylight from sunrise to sunset, then 25 hours of continuous darkness before the sun rises again. The temperature curve of each day tells a story of extremes beginning to dominate. In the old world of 24-hour days, surface temperatures peaked a few hours after solar noon and reached their minimum just before dawn, a relatively gentle oscillation with perhaps a 15 or 20 degrees Celsius range in temperate regions. But now, with 25 hours of continuous solar heating, surface temperatures climb much higher. The ground absorbs energy hour after hour, with no sunset to halt the warming. By the time the sun finally sets, surface temperatures in mid-latitude regions might have risen 30 or 40 degrees above the nighttime minimum. Then comes the long night. 25 hours of darkness. No solar input to maintain temperature. The ground radiates its accumulated heat away to space, steadily cooling. By the time dawn finally arrives, temperatures have plunged, perhaps dropping 30 or 40 degrees from the daytime maximum. The daily temperature range has roughly doubled compared to the 24-hour world, creating swings from pleasantly warm to uncomfortably hot during the day, from cool to genuinely cold at night. This temperature extreme affects everything. Organisms that evolved for relatively stable temperature ranges now face conditions that swing wildly over the course of each cycle. Cold-blooded animals, reptiles, amphibians, insects, whose body temperatures match their environment, struggle particularly. A lizard that could bask in morning sun and remain active all day in the old world now faces a challenge. The afternoon gets too hot for activity, forcing it to seek shelter. Then night arrives and doesn't end for 25 hours, during which temperatures drop so low that the lizard becomes sluggish, unable to hunt or escape predators effectively. Many species would simply go extinct, unable to adapt quickly enough to such a dramatic change in the thermal environment. Others would evolve, but evolution requires generations, and if the rotation is slowing on a time scale of centuries rather than millions of years, evolution can't keep pace. The result would be a mass extinction event, particularly affecting ectothermic species and those with narrow thermal tolerance ranges. Plants face a different set of challenges. 25 hours of continuous sunlight sounds beneficial, all that extra time for photosynthesis, but plants also experience stress from prolonged light exposure. Photosystem 2. The molecular machinery in chloroplasts that captures light energy can become damaged by excessive light, a process called photoinhibition. Plants have repair mechanisms, but these usually operate during darkness. With light lasting 25 hours, the damage accumulates faster than it can be repaired. Moreover, plants depend on darkness for certain metabolic processes. The dark reactions of photosynthesis, the Calvin cycle, don't actually require darkness, but many other plant processes do. Starch breakdown, protein synthesis, flower development, and various hormonal regulations occur primarily or exclusively at night. Stretching the night to 25 hours might seem to give plants plenty of time for these processes, but it's not that simple. Many are triggered by the transition from light to dark, and their duration is regulated by circadian clocks that can't easily adjust to a 50-hour cycle. The result would be widespread plant stress. Many species would struggle to complete their life cycles. Flowering times would become erratic. Pollination, which depends on synchronization between plants blooming and pollinators being active, would break down. Some plant species would adapt, those with more flexible circadian clocks, or those that could evolve new timing mechanisms quickly, but many would decline or disappear. Agricultural crops, bred over millennia for specific day lengths and temperature ranges, would be particularly vulnerable. Wheat, rice, corn, the staples that feed billions, are all photoperiod sensitive and temperature sensitive. A 50-hour day-night cycle would devastate traditional agriculture. Yields would plummet. Some crops might fail to flower at all. Others might grow vegetatively but never produce seeds. Humanity would respond with technology. Massive greenhouse complexes, artificially lit to maintain 24-hour cycles regardless of external conditions, would become essential for food production. These controlled environments would consume enormous amounts of energy to power lights during the long nights and cooling systems during the hot afternoons. But they would work, allowing continued crop production even as the external environment became increasingly hostile to traditional farming. Livestock would retreat indoors as well. Chickens, cows, pigs, all raised in climate-controlled barns where day length could be regulated artificially. The pastoral image of cows grazing in open fields would become rare, limited to hardy breeds in regions where temperature extremes remained manageable. Human circadian rhythms would be severely challenged at this 50-hour day length. Our internal clocks, evolved for 24 4 hours and capable of adjusting somewhat to 20, 5 or even 30 hours, simply cannot synchronize to 50 hours. The suprachiasmatic nucleus, our biological pacemaker, would continue operating on something close to its natural 24-hour period, falling completely out of phase with the external day-night cycle. The result would be chronic circadian disruption for most people. You'd feel sleepy during the external day and alert during night about half the time, as your internal rhythm cycled through phases relative to the external cycle. This isn't just inconvenient, it's genuinely harmful to health. Chronic circadian misalignment increases risks of obesity, diabetes, cardiovascular disease, depression, and numerous other conditions. People would adapt using artificial environments. Buildings would have controllable lighting, windows that could be darkened completely, and climate control that ignored external conditions. You might live in a habitat where day and night followed a 24-hour artificial cycle, lights on for 12 hours, off for 12 hours, regardless of whether the sun was up or down outside. You'd rarely see the actual sun, rarely experience true day or night as defined by Earth's rotation. Cities would transform, with people needing to work and sleep on schedules decoupled from external day-night cycles. There would be no universal daytime, when everyone is active, and nighttime, when everyone sleeps. Instead, shifts would distribute across the 50-hour period. Some people would work during external daylight, others during external darkness, all following personal or organizational schedules that might have little to do with solar position. This would actually provide some economic benefits. Continuous operation of factories, businesses, and services across all 50 hours would be easier than it was in the old 24-hour world. Transportation systems could maintain steady flow, rather than dealing with rush hours. Energy consumption would smooth out, rather than peaking during daytime. But it would come at the cost of disconnection from the natural world. Humans would become creatures of artificial environments, our lives regulated by clocks and artificial lighting, rather than by the sun. Children might grow up rarely experiencing true sunrise or sunset, living their entire lives in climate-controlled spaces where day and night were just settings on a lighting control panel. The night sky would change its character dramatically. Currently, with 12 hours of darkness, astronomical observations and casual stargazing fit naturally into human schedules. But with 25 hours of continuous darkness, the night would feel interminable. Early in the night period, people would still be awake, going about evening activities. But as hours stretched on, 10 hours of darkness, 15, 20, a profound psychological weight would settle. The sun left so long ago, it won't return for hours yet. The darkness begins to feel oppressive, endless. Conversely, the long day would have its own psychological impact. The sun rises, climbs, reaches noon, begins its descent, but so slowly. Hour after hour of sunlight, the sun hanging in the sky, barely seeming to move. By the 20th hour of continuous daylight, even with artificial climate control, people would begin to crave darkness, to yearn for night, for relief from the relentless presence of the sun. Wind patterns would be fundamentally reorganized by this point. The Coriolis effect, now noticeably weaker with Earth rotating more than twice as slowly, would allow air masses to flow more directly from high pressure to low pressure, rather than being deflected into the circular patterns we're familiar with. The jet streams, those high-altitude rivers of fast, moving air that guide weather systems, would weaken and shift. Weather would become more meridional, meaning north, south oriented rather than the current west, east orientation. Storm systems would track differently. The familiar pattern of low-pressure systems moving from west to east across North America and Europe would break down. Instead, storms might move more directly north or south, following temperature gradients that had become more important than rotational effects in determining atmospheric flow. Hurricanes and typhoons, those magnificent and terrible rotating storm systems, would become rare or perhaps impossible. These storms depend critically on the Coriolis effect to maintain their rotation and structure. With rotation slowed to 50-hour days, the Coriolis effect at tropical latitudes would be too weak to generate the spin needed for hurricane formation. This would actually be beneficial, eliminating one category of natural disaster, but it would also remove an important mechanism for transporting heat from the tropics toward the poles. Ocean currents would be reorganizing as well. The great gyres would be weakening, their circulation slowing as the Coriolis effect that maintains them diminished. The Gulf Stream, which currently carries warm water from the Caribbean northeast across the Atlantic, moderating European climate, would be changing course and intensity. Britain and Scandinavia, currently kept surprisingly warm for their latitude by this heat transport, would cool significantly as the current weakened. Tides would still occur, driven by the moon's gravity, but their pattern would change. Currently, most coastal locations experience 2 high tides per day, roughly 12 hours apart, as Earth rotates beneath the tidal bulges. With a 50-hour day, the same location would experience high tide approximately every 25 hours, falling out of sync with the day-night cycle. High tide might occur at noon on one day, night cycle, at midnight on the next, then noon again, in a slowly drifting pattern. In this world of 50-hour days, the boundary between adapted and maladapted becomes stark. Humans, with our technology, could survive and even maintain reasonable quality of life, though at great cost in energy and infrastructure. But natural ecosystems would be collapsing, unable to adjust quickly enough to such extreme conditions. The world would be transforming from a vibrant living planet to something more barren, more hostile, with life retreating to protected enclaves and artificial habitats. Yet even this isn't the end of the journey. Earth's rotation continues to slow. 50 hours is just another milestone. Days will grow longer still, 75 hours, 100. Beyond, each step bringing new challenges, new adaptations, new transformations. Rest now in this understanding. Feel how profoundly day length affects everything: temperature, weather, life cycles, human psychology. Appreciate the perfection of the 24-hour day you actually live with, the gentle rhythm that makes Earth habitable, that allows life to flourish. Let that appreciation deepen your relaxation, your gratitude for the stable rotation you experience every day of your life. Breathe slowly through these imagined extremes, knowing they're just thought experiments, that your world remains stable, your days remain comfortably regular. Let the contrast between this imagined future and your present reality heighten your appreciation for now, for this moment, for the gentle, predictable rotations of the planet beneath you. We push further now into our thought experiment, into a realm so foreign to human experience that it requires conscious effort to imagine. Earth's rotation has slowed dramatically. Days now last 100 hours or more, over 4 of our current 24-hour cycles compressed into a single sunrise to sunrise period, 50 hours of continuous daylight, 50 hours of unbroken darkness. This is a world transformed almost beyond recognition, where the fundamental rhythms that have governed life for billions of years have been replaced by something alien, extreme, nearly incompatible with life as we understand it. Picture yourself, though. Yourself, in any recognizable sense, is becoming difficult to imagine, experiencing such a world. The sun rises, a familiar sight, but occurring in an unfamiliar context. You've been living through 50 hours of darkness, a night so long it's become almost timeless, divorced from any intuitive sense of day and night. Sunrise doesn't feel like the beginning of a new day, but rather like the slow opening of a shutter that's been closed for an eternity. The sun climbs. In the old world of 24-hour days, the sun would reach noon about 6 hours after sunrise. Here, with a 100-hour day, the sun takes 12.5 hours just to climb from horizon to zenith. You could watch it for an entire workday, 8, 9, 10 hours, and it would still be rising, still climbing toward noon, moving so slowly across the sky that its position seems almost fixed. The temperature consequences of this prolonged solar heating are severe. Imagine the hottest summer afternoon you've ever experienced, that peak heat when the sun has been beating down for hours in the ground. The air, everything feels saturated with warmth. Now extend that heating for 50 continuous hours. The ground absorbs solar energy hour after hour with no respite, no cooling night to provide relief. Surface temperatures climb relentlessly. In temperate regions that currently experience comfortable temperature ranges, daytime highs would soar to 50, 60, perhaps 70 degrees Celsius, 120 to 160 degrees Fahrenheit, by the end of the 50-hour day period. These are temperatures incompatible with most life. Water evaporates rapidly at such heat. Vegetation withers and dies. Animals must retreat underground, or find whatever shelter they can, waiting out the scorching day in burrows or caves, where some thermal inertia from the cooler night remains. The tropics would become utterly uninhabitable on the surface. Equatorial regions, which currently receive the most intense solar heating, but benefit from relatively short day-night cycles that prevent extreme temperature accumulation, would turn into furnaces. Surface temperatures could exceed 80 or even 90 degrees Celsius during the long day, well above the boiling point of water at reduced atmospheric pressure. If the atmosphere itself begins to change, then comes the night. The sun finally sets after 50 hours of continuous presence. The relief would be immediate but temporary. The ground begins radiating its accumulated heat away to space. Temperatures drop, but they drop from such extreme highs, and the night is so long, that by the end of 50 hours of darkness, temperatures in those same temperate regions would plunge to 30, 40, perhaps 50 degrees Celsius, -20 to -60 Fahrenheit. This is a temperature swing of over 100 degrees Celsius, from scorching to freezing, within each day-night cycle. No organism evolved on Earth is adapted to such extremes. Even extremophiles, those remarkable organisms that survive in hot springs or Antarctic ice, are specialized for either heat or cold, not both, and certainly not rapid transitions between the two. The atmosphere itself would begin behaving strangely under these conditions. During the 50-hour day, the heated surface would create enormous convective currents, hot air rising vigorously, creating updrafts of tremendous power. Clouds would form at high altitudes as this air cooled and moisture condensed. These wouldn't be ordinary clouds but towering structures, perhaps reaching the stratosphere, representing the atmosphere's desperate attempt to redistribute the heat. During the 50-hour night, the opposite would occur. Cold, dense air would sink, creating powerful downdrafts and stable inversions near the surface. The sky would clear as descending air warmed and its moisture holding capacity increased, causing clouds to evaporate. The atmosphere would stratify into distinct layers: cold, still air at the surface and warmer air aloft, with very little mixing between them. The terminator, the boundary between day and night, would become a zone of extreme weather. Picture this boundary as a permanent storm front circling the planet. On one side, scorching daylight heating the surface, creating updrafts and instability. On the other side, frigid darkness cooling everything, creating downdrafts and stable conditions. Where these two air masses meet, the contrast would generate winds of extraordinary power. These terminator storms would be unlike anything in current weather patterns. Winds might reach hundreds of kilometers per hour, driven by the enormous temperature difference between the day and night sides. Thunder would be constant as the violently rising and sinking air masses created electrical charge separation. Lightning would illuminate the permanent twilight of the terminator zone almost continuously. Rain, hail, possibly even snow and freezing rain simultaneously, as the different temperature regimes mixed chaotically. Any life attempting to survive on the surface would be forced toward this terminator zone, where temperatures remain more moderate, not comfortable, but survivable. Here, where eternal afternoon transitions to eternal evening transitions to eternal night, where the sun hovers perpetually near the horizon, organisms might find refuge. But living in a permanent storm zone has its own challenges. Water distribution across the planet would be radically altered. On the day side, surface water would evaporate rapidly under the intense prolonged heating. Lakes would shrink. Rivers would dwindle to trickles as their water vaporized faster than it could be replenished. The atmosphere would become loaded with water vapor, creating a thick, humid, oppressive air on the day side. This water vapor would be transported by winds toward the night side, where the extreme cold would cause it to condense and fall as rain, sleet, or snow. The night side would become a water collector, accumulating precipitation throughout the 50-hour dark period. Much of this water would freeze, building up as ice sheets on the cold night side surface. Over many day-night cycles, a pattern would emerge: water continually evaporating from the day side, being transported through the atmosphere, falling and freezing on the night side. The day side would become progressively more arid, a desert of heated rock and sand. The night side would accumulate vast ice deposits, perhaps kilometers thick, trapping water that evaporates when that ice rotates into daylight again, only to be transported back to the current night side in an endless cycle. The ocean would participate in this redistribution. Deep ocean water has thermal inertia. It doesn't heat or cool as quickly as the surface, so the ocean would serve as a thermal buffer, moderating extremes somewhat. But surface layers would still heat dramatically during the day and cool substantially during the night. Ocean currents would be completely reorganized, driven now more by temperature differences than by the weakened Coriolis effect. Upwelling and downwelling would dominate ocean circulation. On the day side, heated surface water would become less dense and resist sinking, creating a stable stratified layer. On the night side, surface cooling would make water denser, causing it to sink and driving deep circulation. The ocean would breathe with the day-night cycle, mixing and stratifying in rhythm with the 100-hour rotation. Marine life would face catastrophic challenges. Many marine organisms are sensitive to temperature changes of just a few degrees. Swings of 30, 40, or 50 degrees between day and night would be lethal to most species. Coral reefs, already stressed by current climate change, would bleach and die as water temperatures oscillated between too hot and too cold. Fish would be forced to migrate constantly, following temperature zones as they rotated with the planet. never able to settle in one location. Some organisms might survive in the deep ocean, where temperature remains more stable, insulated from surface extremes by hundreds or thousands of meters of water. The deep sea, currently one of Earth's most stable environments, might become the last refuge for complex life, a dark world of thermal vents and pressure, adapted creatures carrying on while the surface world transforms into a hellscape of extremes. On land, humanity would have retreated almost entirely underground, or into heavily fortified structures. Surface habitation would be impossible without technology. Living spaces would be buried beneath meters of insulation to buffer against the temperature extremes. Energy consumption would be enormous, cooling during the day, heating during the night, artificial lighting to maintain any semblance of normal circadian rhythms. Cities might be built in vast underground caverns, artificially lit and climate-controlled, with only minimal surface infrastructure for energy collection and resource extraction. Solar power would actually be abundant. 50 continuous hours of sunlight provides enormous energy, if you can capture and store it. But the engineering challenges of surviving surface conditions long enough to maintain solar panels would be significant. Alternatively, settlements might cluster in the Terminator Zone, that band of permanent twilight and permanent storms. Here, temperatures would be more moderate, averaging the extremes of day and night sides. The storms would be dangerous and the wind relentless, but with robust enough architecture, perhaps inspired by offshore oil platforms or Antarctic research stations, humans might maintain surface communities. These Terminator settlements would be mobile, or at least modular and relocatable. As Earth rotates, the Terminator Zone moves across the surface. A settlement would need to migrate, following the twilight zone around the planet to maintain its favorable thermal position. Alternatively, a network of settlements could be distributed around the globe, with populations rotating between them as each site moved through its optimal phase relative to the sun. Agriculture would be entirely artificial by this point. No crops could survive the surface conditions. All food production would occur in controlled environments, underground farms with artificial lighting, hydroponic or aeroponic systems that minimize water use, carefully regulated temperatures and atmospheres optimized for plant growth. The variety of available crops would narrow to those species and cultivars that could thrive in these artificial conditions. Livestock would be similarly confined. Animals raised for food would live their entire lives in climate-controlled facilities, never seeing the sun or experiencing true day or night. The ethical implications of such intensive confinement would be debated, but survival would take precedence. Alternative protein sources, cultured meat, insects, microorganisms, might become dominant as more efficient than raising traditional livestock in such constrained conditions. The psychological impact on humans would be profound. Humans evolved as diurnal creatures, adapted to wake with sunrise and sleep with sunset, to organize our lives around the day-night cycle. In this world of 100-hour days, that connection would be completely severed. Time would become abstract, measured by clocks, but divorced from any natural rhythm. Mental health challenges would likely increase. Seasonal affective disorder, currently linked to reduced daylight in winter, might become endemic as people lost contact with natural light cycles. Depression, anxiety, sleep disorders, all currently influenced by circadian disruption, would require aggressive management through medication, light therapy, and other interventions. Yet humans are remarkably adaptable. Communities would establish new rhythms, artificial but meaningful. Perhaps a 20, 4-hour cycle maintained through lighting and social conventions, allowing people to maintain their natural circadian rhythms, even though external conditions bore no relationship to that cycle. Work schedules, meal times, social gatherings, all would follow internal community time rather than solar time. Children born into this world would know nothing else. To them, the 100-hour day would be normal, the way things have always been. Stories of the old earth, where days were short and night brought welcome rest every 12 hours, would seem like mythology, impossible to truly comprehend. They would adapt to artificial environments as their natural habitat, to controlled climates as the default, to a sun that appeared only briefly or not at all as normal. This advanced phase of rotation slowdown represents a fundamental break from Earth's history as a living planet. The conditions have moved so far from what life evolved to handle that natural ecosystems have largely collapsed. What remains is life in artificial refuges, heavily dependent on technology, maintaining a precarious existence on a world that has become hostile to its own biological heritage. And yet, even this extreme isn't the end point. Earth's rotation could slow further still, approaching the ultimate limit, complete tidal lock, where rotation ceases entirely relative to the sun, where one hemisphere experiences eternal day and the other eternal night. That final state awaits us in the next part of our exploration. For now, rest in the understanding that this 100-hour day is still just imagination, still just physics extrapolated to an extreme that won't occur for billions of years, if ever. Your world remains stable, your days remain comfortably brief, your nights arrive with reassuring regularity. Let the contrast between this imagined extreme and your actual gentle reality deepen your appreciation for the perfect rotation you enjoy right now. Breathe slowly. Feel the solid, stable ground beneath you. Trust in the reliable rhythm of Earth's current spin. Let these extreme possibilities drift away like dreams, leaving only calm comfort. Let's step back now from the extremes of 100-hour days and examine more carefully what happens to Earth's atmosphere as rotation slows, the winds, the weather patterns, the entire circulation system that distributes heat and moisture around the planet. Understanding these atmospheric changes helps us appreciate just how profoundly rotation influences the world we know, and how dramatically things would shift as that rotation diminishes. Begin with the Coriolis effect, that subtle but crucial consequence of Earth's rotation. Named after French mathematician Gustave de Coriolis, who described it mathematically in 1835. This effect is perhaps the most important way rotation influences atmospheric behavior. It's not a force, exactly, nothing pushes on moving air, but rather an apparent deflection that occurs when observing motion from a rotating reference frame. Picture yourself standing at the North Pole, looking down at Earth rotating beneath you. From your perspective, the planet spins counterclockwise, completing one rotation every 24 hours currently. Now imagine air moving from the pole toward the equator. As this air moves southward, it's also moving from a region where Earth's surface has almost zero rotational velocity to regions where the surface is moving eastward at increasing speeds. The air mass retains its original eastward velocity, the velocity it had at the pole, which is nearly zero. But the ground beneath it is moving faster and faster eastward as it approaches lower latitudes. From the ground's perspective, the air appears to be deflecting westward, even though it's actually moving straight in inertial space. This is the Coriolis effect. Objects moving north or south appear to curve westward or eastward, due to the changing rotational velocity of the surface beneath them. The magnitude of this deflection depends directly on rotation rate. Faster rotation means stronger deflection. Slower rotation means weaker deflection. The mathematical relationship is linear. Have the rotation rate, and you have the Coriolis effect. This means that as Earth's rotation slows through our thought experiment, the Coriolis effect weakens proportionally. Currently, with a 24-hour day, the Coriolis effect is strong enough to dominate large-scale atmospheric motion. Air doesn't flow directly from high pressure to low pressure, as you might intuitively expect. Instead, it curves, flowing roughly parallel to pressure contours, creating the circular patterns we see on weather maps. High pressure systems rotating clockwise in the northern hemisphere, low pressure systems rotating counterclockwise. This deflection creates the jet streams, those rivers of fast, moving air that flow generally west to east at altitudes of 10 to 12 kilometers. The jet streams exist at the boundary between tropical air masses and polar air masses, where the temperature gradient is steepest. Without Coriolis deflection, air would simply flow from the warm tropical regions toward the cold polar regions. But with strong Coriolis effect, this north-south flow is deflected into west-east flow, creating the jet streams that guide weather systems across continents. As rotation slows and Coriolis effect weakens, these jet streams would slow, weaken, and eventually disappear. At a 50-hour day, with Coriolis effect reduced to less than half its current strength, the jet streams would be noticeably weaker, their paths more variable. At a 100-hour day, with Coriolis effect down to roughly a quarter of current strength, the jet streams would barely exist as coherent features. Weather patterns would transform in response. Currently, mid-latitude weather is dominated by the passage of high and low pressure systems carried along by the jet stream, moving generally from west to east. In North America, weather systems develop in the Pacific, move eastward across the continent, and exit into the Atlantic. In Europe, systems develop in the Atlantic, cross westward over the continent, and continue into Asia. This west to east progression is so reliable that it forms the basis for weather forecasting. With weakened Coriolis effect, this pattern would break down. Pressure systems would move more directly from high pressure to low pressure, following temperature gradients, rather than being steered by rotation. Weather would become more meridional, moving north-south, and less predictable in terms of west-east progression. Storm systems themselves would change character. Currently, mid-latitude cyclones, those large low-pressure systems that bring rain and snow, develop their rotation from the Coriolis effect. Warm air from the south meets cold air from the north along a frontal boundary. The temperature difference creates pressure gradients, and the Coriolis effect converts this into rotation. The system spins up, developing a characteristic comma shape visible in satellite images. With counterclockwise rotation in the northern hemisphere, weaker Coriolis effect would make it harder for these storms to develop organized rotation. They might still form. Temperature contrasts would still create pressure gradients, but they'd be less coherent, less organized, perhaps shorter-lived. The beautiful spiral patterns of mid-latitude cyclones might give way to more amorphous weather systems, harder to track and predict. Hurricanes and tropical cyclones would be even more profoundly affected. These magnificent storms absolutely depend on Coriolis effect for their existence. They form over warm tropical oceans where temperature gradients are minimal. There's no cold polar air to create frontal boundaries. Instead, they develop from small disturbances that begin to rotate due to Coriolis effect. As the rotation concentrates, it creates low pressure at the center, which draws in more air, which rotates faster, which creates lower pressure, in a positive feedback loop. But this only works if the Coriolis effect is strong enough to initiate and maintain rotation. There's actually a threshold. Hurricanes don't form within about 5 degrees of the equator, because the Coriolis effect there is too weak. As Earth's rotation slows, this hurricane-free zone would expand. At 25-hour days, it might extend to 10 degrees latitude. At 50-hour days, perhaps 20 degrees. At 100-hour days, hurricanes might not form at all anywhere on the planet. This would eliminate one of Earth's most destructive weather phenomena, which might seem beneficial. But hurricanes serve an important function in Earth's climate system. They transport enormous amounts of heat from the tropics toward higher latitudes. A single hurricane carries as much energy as several years' worth of human energy consumption. Without hurricanes, the tropics would warm even more, and heat distribution toward the poles would be less efficient. The general circulation of the atmosphere, the large-scale patterns that transport heat from equator to poles, would reorganize completely. Currently, this circulation is divided into 3 cells in each hemisphere: the Hadley cell in the tropics, the Ferrel cell in mid-latitudes, and the polar cell in high latitudes. This 3-cell structure exists because of the Coriolis effect. Without Coriolis deflection, we'd have a simpler patterns, one large convection cell in each hemisphere. Warm air would rise at the equator, flow at high altitude toward the poles, cool and sink at the poles, then flow back along the surface toward the equator. This is actually what happens on slowly rotating planets like Venus, which has a day longer than its year. Earth would transition toward this simpler pattern as rotation slowed. The 3-cell structure would gradually collapse into something simpler, with more direct north-south flow and less of the complex west-east circulation that currently characterizes our weather. The trade winds, those reliable easterly winds in the tropics that guided sailing ships across the oceans, would weaken and potentially reverse direction as Hadley cell circulation changed. The westerlies, the prevailing west to east winds in mid-latitudes, would weaken and become more variable. These winds currently drive ocean currents like the Gulf Stream and the Kuroshio Current. As they weakened, those ocean currents would weaken too, reducing heat transport from tropics to higher latitudes and allowing temperature contrasts to increase.